welcome to Lessons in Logic video number 34, which I hope will be a lot shorter than video 33. And in this video, we're going to do a little more practice with truth tables, but also study some famous forms in statement logic, some famous argument patterns. Now, this video will assume a lot of background knowledge. Go back and review from earlier videos as much as necessary. For the moment, I think I will resist the urge to review, except to say that, remember this, when we are using lowercase italicized letters, we're symbolizing any proposition. And so what I have here, this on the screen right here, this P wedge Q tilde P, therefore Q, is where those letters are lowercase, symbolizing all arguments that have this pattern, because those letters symbolize any proposition. But if these were capitalized and not italicized, then they would symbolize specific propositions, and the whole thing would symbolize a specific argument. Like if I had A wedge Q, tilde A, therefore Q, and it, or P wedge Q, tilde P, therefore Q, or A wedge B, tilde B, therefore Q, and they were all capitalized and not italicized, then those would represent specific statements and a specific argument. Here we are representing an argument pattern, not a specific argument, but all arguments that have this particular pattern of reasoning. Okay, so now let's just symbolize these with truth tables and be done. Good practice with truth tables, good opportunity to review some famous forms and see how they work. That's all we're doing. Now, using the custom I'm adopting in this series, at least, we bold our guide columns where we lay out all the possibilities for truth table. All the possibilities for whether the premises of an argument. All the possibilities for whether the different atomic propositions in the argument are true or false. And then we use the therefore symbol for the conclusion column, and then we have one column for each premise. Now we make half of our rows represent situations in which the first atomic proposition is true, and then half for situations in which the first atomic proposition is false. Then we do the same thing over here, but in an orderly fashion. It would do us no good to do this, because then we would just have a lot of redundancy. We'd have two rows representing situations where everything's true and two rows representing situations where everything's false, and it would be ridiculous. We wouldn't even have what we need. What we do is, to lay out all the possibilities, we alternate in that last guide column. So true, true, false, false, true, false is what we want when we have only two atomic propositions to chart. So P wedge Q is true when P or Q is true, because P wedge Q means either P or Q. It's only false when they're both false. Tilde P has the opposite truth value of P, so where P is true, the denial of P, tilde P being the denial of P, where P is true, the denial of it is false. And then Q, well, Q is going to follow what we have in its own guide column. It's just a repetition of that. So now, do we have any rows on this table where the premises are true, the conclusion false at the same time? Doesn't look like we do. In this row, we have a false conclusion, but one of the premises is also false. Similarly, in this row, but a different premise, we have a false conclusion, but also a false premise. So it's not possible for the premises to be true and the conclusion false at the same time. And by making this truth table, we have demonstrated that no argument using this pattern can have true premises and a false conclusion at the same time. And therefore, any argument using this pattern is a valid argument, which is a wonderful thing for an argument to be. All right, let's repeat and look at another pattern. Hypothetical syllogism pattern is P horseshoe Q, Q horseshoe R, therefore P horseshoe R, which is if P then Q, if Q then R, therefore if P then R. Plan your guide columns to cover all the possibilities for P being true or false and Q being true or false. And then P wedge Q, P horseshoe Q, if P then Q is going to be true except when P is true and Q is false, which means true, false, true, true for those four rows. Q wedge R, Q horseshoe R, if Q then R is going to be true except when, oh, silly me. Whoa, horrible mistakes. We've got three atomic propositions. Did everything wrong here. I need a whole other row. No, I need a whole other column. I need a whole other guide column for R. What was I thinking? How did I botch that? So let's add some rows. Sorry. So now we have one row for each atomic proposition. And for the first row, we make half the columns true. Sorry, for the first atomic proposition, we make half the columns true, and the next false. For the next one, we make half of that first batch of trues true, and the next half false. And then half of that first batch of falses true, the next batch false. And then the third and final guide column, we alternate. Okay, so now back on track. P horseshoe Q is true whenever Q is true or P is false. So it's going to be true here because Q is true, and it's going to be true here because P is false. In other words, if P then Q is true except when P is Q and true is false. A conditional proposition is true except when the if clause is true and the then clause is false. Similarly, but we have to look at different columns here. Q horseshoe R. Let's see, Q horseshoe R. Q horseshoe R is going to be true except when R is false and Q true. So it's true here. It's false here. It's true here. It's false here. It's going to be true here and false here. Q horseshoe R. Yep. And then where Q is false and R is true, if Q then R is considered true. Okay, P horseshoe R. It's going to be true except where P is true and R is false. So P and R are true and false in our first two rows of the truth table, and then true and false again in our next two rows of the truth table. And then the next four rows, the antecedent is false. So we can't say the conditional proposition is false, so we have to say it's true. And now, do you have any rows in this truth table with true premises and a false conclusion? Well, here we've got a false conclusion, but one of the premises is false. Here we have a false conclusion, but one of the premises is false. And there's a true conclusion everywhere else. In other words, there are 8 possibilities for whether the pieces of any argument having this pattern, hypothetical syllogism, if X then Y, if Y then Z, therefore if X then Z, if P then Q, if Q then R, therefore if P then R. There are 8 possibilities, one for each row of this truth table, 8 possibilities for whether the X, Y, and Z, the P, Q, and R, the different atomic propositions in that argument are true or false. And in not one of them is it possible to have true premises and a false conclusion, therefore the argument is valid. Any argument having this pattern is valid. Now, modus ponens, this should be pretty easy. Modus ponens is P horseshoe Q, P, therefore Q. We're going to lay on our guide columns the same as we did for our earlier 2 atomic statement pattern. And now P horseshoe Q is true. If P then Q is true, except when P is true, Q is false. In other words, true, false, true, true is what we put in our column here for P horseshoe Q. If P then Q is true, except when the if bit is true and the then bit is false. And P and Q, well, here we could just copy what was in our other columns. Now, do we have any row with true premises and a false conclusion? The only way the conclusion can be false is if one of the premises is false. Therefore, modus ponens is a valid argument form. No argument using this pattern will ever have true premises and a false conclusion. It cannot be done. You'd have an easier time, for example, cutting down the mightiest tree in the forest with a herring than making an argument with true premises and a false conclusion, having the modus ponens pattern. Now, modus tollens, this is going to be very similar. I'm just going to copy and paste and then make whatever adjustments seem necessary. Okay, so yes, we're just going to switch around the P and Q in our premises here and add tildes. If P, then Q, not Q, therefore not P, or P horseshoe Q, tilde Q, therefore tilde P. And so now we have to adjust these two columns. How many rows we have added here for no reason. The copying and pasting just doesn't always work out. And it's really annoying me, so I'm going to delete them. I hope that was the last one. I thought it would be. I really did. There we go. So tilde Q is going to have the opposite truth value of Q. So instead of TF, we're going to have FTFT. And then tilde P has the opposite truth value of P because it's a negation of P. Tilde P means not P. Therefore, anytime a proposition symbolized by P is true, its denial is going to be false and vice versa. Now, do we have any row with false premises and a true conclusion? No. The only way it's possible for the premises to be true, the only way it's possible for the conclusion to be false is if one of the premises is false. There is no possibility that a modus tollens argument, that an argument with this pattern will have true premises and a false conclusion. It cannot be done. Denying the antecedent. Well, again, we can copy and paste and then make some adjustments. Denying the antecedent is going to be if P, then Q, not P, therefore not Q. Oh, what an ugly typo. Denying the antecedent. If P, then Q, not P, therefore not Q. P horseshoe Q, tilde P, therefore tilde Q. So our first columns are totally the same, nothing different at all. Now our tilde P column is going to be the opposite of P. Where P is true, its denial is true. Where P is true, its denial is false. Where P is false, its denial is true. And then where Q is true, its denial is false. Where Q is false, its denial is true. So opposite truth values again. And now, do we have true premises and a false conclusion anywhere in this argument? In other words, is it possible to have is it possible to find a situation where the premises of an argument having this form are true and the conclusion false at the same time? Yes, it is possible. Ta-da! Behold! On this third row, when P is false and Q is true, it's true that if P, then Q. And it's true that not P, but it's false that not Q. Therefore, this is an invalid argument. It's possible to have true premises and a false conclusion. And one more famous form. Let's see. I guess, again, we'll copy and paste. Let's see if I can avoid having those extra columns by copying and pasting the whole chart rather than copying and pasting data into the chart. And having copied and pasted, we make some adjustments. Affirming the consequent is the pattern. If P, then Q, Q, therefore P. And filling in with the data, which is just the same as it is in the guide columns, we have this chart. We have P horseshoe Q, Q, therefore P, and we have T's and F's as so, and there is a situation with true premises and a false conclusion. In a scenario, once again, where P is true, no, where P is false and Q is true, it's true that if P, then Q. If P were true, then Q would be true. That's true, still considered true. And it is true that Q and false that P, therefore, an argument having this form is invalid. Now, having said that, do be careful. When you have these invalid argument forms, there's always a small possibility, unless you've been really careful, that an argument that you found has this form is still valid. That it's still not possible for an argument having that form to have true premises and false conclusions. What I should say is an argument having this pattern, affirming the consequent, often will have true premises and a false, will have the possibility of true premises and a false conclusion. I should say that differently. What's true is there are many arguments having this pattern that have true premises and a false conclusion, but it is possible to have an argument with this pattern that has no possibility of true premises and a false conclusion, because an argument can have more than one pattern. Every argument with one of these valid patterns is a valid argument. There's no chance of having true premises and a false conclusion. Modus Ponens, Modus Tollens, hypothetical syllogism, and disjunctive syllogism. But with denying the antecedent, affirming the consequent, we're dealing with patterns of arguments such that many arguments have that pattern and can have true premises and a false conclusion. But some arguments might have this pattern and have another pattern because arguments have more than one pattern. Remember, every argument has a general pattern and a very specific pattern, and often a lot of patterns in between. The simplest pattern of an argument is always premise, premise, conclusion, or premise, conclusion, or premise, 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 conclusion, or whatever, depending on how many premises there are. Every argument with a valid form is a valid argument. Not every argument with an invalid form is necessarily invalid. The specific form of an argument is its most detailed form, its most detailed pattern. For a valid argument, its specific form is always valid. And I think we could safely say for an invalid argument, its most specific form is, for an invalid argument, its most specific form is invalid. But every valid argument has at least one invalid non-specific form. There's a typo here, which I'm now fixing. No valid argument has an invalid specific form. All the arguments with an invalid specific form are invalid arguments. Now, let me just illustrate. Let me find for you an argument that has this pattern. Remember, P and Q, when they're lowercase, represent any proposition. So here's an argument that's invalid, having this pattern. I'm going to make two, one that's valid, one that's invalid. Here's an argument that's invalid, having this pattern. If P then Q, if an invalid one. If, well, standard example for me. If it is raining hard now, then the grass is wet. Actually, I don't know if I can see any grass from here, but let's say sidewalk. There's definitely a sidewalk you can see from that window. So right now, it's true that if it's raining hard, then the sidewalk is wet. And it's true that the sidewalk is wet, but it's false that it's raining hard. So that's obviously an invalid argument. But what if P were symbolizing as it does symbolize, because it symbolizes any proposition we need it to? When it's a lowercase italicized, what if P were symbolizing something else? Let's see. What if it were symbolizing, in fact, some complex proposition? Complex propositions such as, well, let's first fill in the pattern in ordinary language. If P, then Q is what P horseshoe Q means. Good. So now let's replace P with the right kind of proposition. And what I want is a tautology. In fact, I was going to say either there is T in my teacup or there is not. That would work just fine. And then I thought maybe I should just do a simpler tautology from statement law, from propositional logic stuff, from categorical logic stuff. All unmarried men are bachelors or some such. Now let's do either. Let's do the complex proposition. If either there is Mark's teacup, if either there is T in Mark's teacup or there is not, then Q. Q, therefore, either there is T in Mark's teacup or there is not. So now you can fill in Q with anything you like. Well, to have a true premise, ought to be some sort of true thing. Yes, we're looking for a situation with, yeah, we need a true premise. Hang on, let me try to find a simple true premise. Mark likes tea. Sure, why not? Now, if you don't think this is a true premise because there's no connection between either there being tea in my teacup or not and me liking tea, go back and watch the earlier video where we talked about the truth functional interpretation of compound propositions. It might have been the first video. If not, it was probably the second video in the statement logic subunit. Okay, so maybe I should find a simple one with a connection. Where we don't have to worry about that truth functional interpretation of compound propositions. I got it. I think I know how to do it. So if you think this isn't true because you don't accept that truth functional interpretation of compound propositions, you're a real stickler for logic should stay closer to ordinary language or something like that. Okay, whatever, fine. We'll finish going over this example and then we'll give you one that should work for you. But in this example, we have the very standard way of thinking in logic, not the whole of how language works, but a good minimal interpretation of language that will help us find out whether arguments are valid or not. And I think we'll never fail in that respect. In this way of using language, we say this premise is true. If there's either tea in Mark's teacup or not, then Mark likes tea. That's true. Because it's true that Mark likes tea. So it's not false that if one, then the other. So, well, because it's considered true unless the antecedent is true and the consequent false. If the if clause is, unless the if clause is true and the then clause is false, the proposition is true. So anyway, the premise is true. And this other premise is true, I do like tea. So now, is it possible to have true premises and a false conclusion? No, because this is a tautology. This conclusion, either there's tea in Mark's teacup or there is not, can't be false. It's the statement is true or it's false. Every statement is true or false. So there's no avoiding this one being true. So this is actually a valid argument, but its specific form is not this. This affirming the consequent form is one form the argument takes, but the argument's form is actually, its specific form, I mean, either P or not P. If either P or not P, then Q. Q, therefore, either P or not P. And since that conclusion, either P or not P, can't be false, the argument ends up being true anyway. Now let's use a simple example, borrowing a bit more now from categorical logic. All guinea pigs are fuzzy. Well, maybe some guinea pig got shaved. All guinea pigs are mammals. If all guinea pigs are mammals, then anything that's a guinea pig will also be a mammal. There you go. So guinea pigs are pretty much defined as a type of mammal. So I don't think this statement can be false. Now, I gotta pause and ask myself, well, what if we reclassify guinea pig someday? Let's do a slightly simpler one then. That should work. Let's go back to the old standard tautology definition. All unmarried men are bachelors. If all unmarried men are bachelors, then anything that's an unmarried man will also be a bachelor. If all unmarried men are bachelors, then anything that's an unmarried man will also be a bachelor. Anything that's an unmarried man will also be a bachelor. Therefore, all unmarried men are bachelors. That argument does have the same pattern, the affirming the consequent pattern, but also it cannot have true premises and a false conclusion at the same time, because the conclusion can't ever be false. The conclusion is what we call a tautology, a statement that can't be false. So this argument is actually valid because of its specific argument form. And it's got one invalid form, but no problem. Anyway, the point is, if you can, as much as you can, pay attention to the fact that arguments have more specific forms and less specific forms, and it's the specific form that really counts. All right, let's quit. Let's end this video, and I'll see you next time. Thanks for watching.